Let's start. So today we will say a little more about the Heisenberg Algebra and about generating functions, which will be the main tool we will use to deal with to actually compute things in the Heisenberg Algebra. So, okay. But also, so tomorrow at 2 p.m. Paris time, which unfortunately is 8 a.m. Toronto time, I'm giving a talk on a subject completely unrelated to this course, though somewhat related to what Jessica has been working on before, and it's at http://drobn.net/KOS21. This is lowercase, not uppercase. Okay? So let me remind you where we were. So whatever we did with finite dimensional algebras, for some reason I want to do with an infinite dimensional algebra. And a priori that seems like a bad idea, but you'll see that it isn't. Okay? So the algebra, the first example of an algebra that I want to work with, and in fact this is going to be a moderate success, but there will be but not a full success. Okay. Anyway, that's the Heisenberg algebra, which is the algebra generated by two symbols p and x, modulo the relations that their commutator is equal to 1. So strictly speaking, I should be calling them p hat and x hat to separate them from other things that will appear later. Often I will be confused and forget to put the hats, and then it should be understood from the context whether it's with hat or without hat. Okay? So within that algebra, I claim that there is a spinor element, a C, and an R element, R, which satisfy all the requirements to make a knot invariant, except not only we don't have the tools to compute this invariant, we don't even have the tools yet to prove that these elements have the required properties. But we will. Okay? So the elements are Ci, which is e to the t over 2 times 1, and strictly speaking, it's not in the algebra, it's in, well, I've put a subscript I to say that it's in tensor factor I, but there is only one tensor factor here, so it really doesn't matter. But it's in the algebra extended by a tiny parameter t. Tiny just means you take power series in it, and it makes sense, okay? Likewise, there is an Rij. Rij lives in two tensor factors labeled hi and labeled I and j. And, well, it should be boldface, sorry, blackboard bold H. And again, with a t parameter, and it's given by e to the t over 2 t pi minus pj times xj. And again, the way to understand this, so this thing here is pi tensor 1 minus, so this is really pi tensor 1 minus 1, or p tensor 1 minus 1 tensor p times 1 tensor x, if you use standard notation, where I is the first tensor factor and j is the second tensor factor. Okay. So how do we work with things like that? So working with non-commutative algebras is difficult, but fortunately, as a vector space, the algebra is isomorphic to a commutative algebra. Just as a vector space, so the multiplication is strange, but as a vector space, it's isomorphic. And this is the content of the PBW theorem, which again is much more general, and later we will see it in other contexts, but for now, I'm just stating it without proving it. If you Google PBW theorem, you'll find how to spell Poincare-Birkhoff-Witt, and you'll find lots of proofs. It's a standard theorem in Lie algebras. So the theorem says that the map from commutative polynomials in P and X, maybe to emphasize that these aren't hats, I'll put inverse hats on them. So these are just commuting variables. So the map from the polynomial ring in two variables into H, given by p to the k x to the L goes to p to the k x to the L, but these have different meanings. These are commuting variables and these are non-commuting variables. So here the order matters. Here the order doesn't. This is the and this is the ordering map in which you place the p's before the x's. So the claim is that this is an isomorphism of vector spaces. And then, if it's an isomorphism of vector spaces, we will want to, or if our strategy is to switch to use this map so as to work with this instead of with that, then the two biggest tasks will be to import these two elements from here to here, and the harder thing is there is a multiplication here. It's an algebra. So we have to import multiplication to here. We have to see what the multiplication law of H is in these terms. And then everything will be written in terms of polynomials, and we will have to work hard to understand how to work with polynomials, but that's a different piece of work. Okay? Good. Okay. What is CI if you pull it back via O? Well, CI is just a power series multiplying 1, so you're just pulling back 1. But the pullback of 1 is just 1, right? The ordering maps 1 to 1. So pulling back CI is not an issue. The only issue is how to pull Rij. So the claim is that Rij is the ordering of the function psi written here, where this is psi. And the only way psi is different from the original formula is that instead of t, you have e to the t minus 1. Okay? That's not a general fact. Okay? That's just, this happens to be the case for this psi. For this element, Rij. So, let's prove it. And so the proof is a bit technical, but later, we have to build up and sort of more interesting things will come later. So let's call Rij phi 1, and let's call the right-hand side of this equation phi 2, and we need to show that phi 1 and phi 2 are equal. So we will show that phi 1 and phi 2 satisfy the same differential equation. So, maybe it's technical, but these are techniques that we will need, techniques that we will use a lot. So, I don't know, surprise, right? We're doing knot theory, but we need differential equations. Okay? So we will say that phi 1 and phi 2 both satisfy the same ordinary differential equation. And the ordinary differential equation is the partial derivative, the derivative of phi with respect, so phi being either one, with respect to t is equal to pi minus pj times xj times phi. And phi at t equal to 0 is 1. So there is a uniqueness and existence and uniqueness statement about solutions of ODEs. And if you have a differential equations, well, which implies that if two things solve the same equations, then they have to be equal. Strictly speaking, this uniqueness and existence theorem is on finite dimensional spaces. So what you can do is mod out this space, or restrict your attention to the subspace of H generated by, or that has only polynomials up to degree 7. Only multiples of P and X up to degree 7. And then you have uniqueness within this. And then replace 7 by 19 and you have uniqueness up to degree 19. And you can just repeat it and you get uniqueness overall. So I want to concentrate on deriving this. Okay? So why is this true? So, okay, this one is trivial. So if you take Rij and substitute t equals 1, you immediately see you get 1. There's nothing to check. Likewise, on the right-hand side, if you set t equals to 1, you get e to the 1 minus 1. Well, it works. Okay? So this one is, so the fact that phi 1 and phi 2 both satisfy this, no green. You know, check marks should be with green. Okay. So this is easy. So I just need to check this one. So let's call this star. So let's check star for phi 1. So for phi 1, oops, I have it wrong, sorry. I have to multiply this by e to the t over 2. But e to the t over 2 is just a multiple of the identity. So really what I want to say, sorry, sorry. That was a formula not for Rij, but for Rij with the first factor removed. But it's a central factor. So really, sorry, so I want to say e to the minus t over 2r is equal to this. Sorry, so if you really want r, you just have to multiply by e to the t over 2. But e to the t over 2 is a multiple of the identity. You can bring it in anywhere. You can it commutes with everything. Sorry. So all I have to do is to compute the derivative of with respect to t of phi 1. But this is the derivative with respect to t of e to the t pi minus pj xj. This is all in a non-commutative world. But it doesn't matter. The derivative is defined, exponentiation is defined so that the derivative is the normal derivative of an exponential function. So this is pi minus pj xj times the exponential function e to the t pi minus pj xj. But this is just what I wrote. everything here should have hats. So this is just what I wrote. So this is done. Okay? But now comes the harder thing. So the harder thing is to differentiate the right-hand side with respect to t. So I want to differentiate phi 2 with respect to t. So this is the derivative with respect to t of the ordering map of ordering p ahead of x in e to the e to, you know what, let me just write psi, in psi. Maybe I should emphasize that psi depends on t. Okay? So, okay. Differentiation with respect to t commutes with ordering p and x. These are completely independent operations. So this is the ordering with respect to ordering in the order p and x of the derivative. Wait, am I messing up? Yeah, no, I'm not messing up. Sorry. The derivative with respect to t of psi t, well, psi t is given explicitly, so I can just differentiate. Okay? So this is ordering p's ahead of x's of the derivative, and I think it comes out to be e to the t pi minus pj xj psi t. So let's see, if I differentiate this with respect to t, I need to differentiate the exponent with respect to t. I think it's just that. Yeah. Okay. So that's the left-hand side of the equation. Now I need to look at the right-hand side. So now I need to look at pi hat minus pj hat xj hat multiplying the ordering of ordering p's ahead of x's of psi t. Right. Okay. So this is a bit challenging. So I want to write this. Okay, this is a product in the algebra. But I want to write it as something in the image of the ordering map. So I want to write it as O of something. Okay? So I need to bring these things into the O. Bring the things that are outside into the O. So let's first bring the x into the O. So this is pi hat minus pj hat times O of what? Let's think about it. So I want to multiply x into some function of p and x, where the p's are written ahead of the x's. Okay? So basically I want to multiply x into p, x, 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 and what I need to do is to bring the x in place. Okay? So every time so basically I need to commute the x across the p's. Every time I commute an x across a p, I pay a price. So x times p is equal to, let's see, p, so this relation over here says px minus xp is equal to 1. So said differently, xp is equal to px minus 1. Okay? So xp is equal to px minus 1. So every time I commute an x across a p, I get two contributions. One contribution is, well, x moves to the other side. That's this one. And the other contribution is a negative 1. If I got the negative 1, the result is already ordered. And if I didn't get a negative 1, so if I just move the x to the other side, then I need to move it across the next p. So basically, what I will get is, at the end, x will move all the way to the other side. So I will get p, 5 p's, and then 4 x's instead of just 3. So this is the contribution like from always moving to the other side. But I will also get a contribution with minus sign, in which is the sum of all possibilities of replacing p by 1. But what is the sum of all possibilities of replacing p by 1? This is differentiating with respect to p. Right? This is exactly what differentiation does. So this is the derivative with respect to p of p, x, x, x. So here we will get exactly that. We will get x times psi t minus the derivative with respect to p of psi t. I hope I got the signs correctly. Yeah, sorry, except this is xj. We're bringing in an xj, and this is the derivative with respect to pj. So, but this can be computed explicitly. So psi is given explicitly, and I can just compute what's inside. I can compute the derivative with respect to pj of psi.
Sorry, just a
yes.
question. So, are we dealing with the x and p's in H or in the Q?
What?
So this x's you've written, I thought they commute.
No, so the calculation is happening. Okay. Yeah, it's confusing. These are the non-commuting ones. These are the non-commuting ones. Or you know what? No, let's write it this way. This is x hat times O of this. O of this, if you order a function, so suppose the function is p to the 5 x cubed. Ordering this function means that you put hats everywhere. This relation is the relation between the hatted variables. Here you have hats everywhere. But this is but now this is an ordered expression. So this is really O of x times f minus the derivative with respect to p of f.
I see.
Okay? Sorry, not this O, Blackboard O. Okay. So, Blackboard bold O, right, sorry. So, but now I can compute this explicitly, and I did it at home, so I will not do it again. You know what, I will not even do it, okay? Because the next step is I need to bring the p's in. But bringing the p's in is trivial, because the p's are on the, because when you normal order these, all p's are on the left. So bringing the p's just appends them on the left, so they just multiply the commutative thing by p. So this is O of pi minus pj times x psi t minus xj psi t minus the derivative with respect to pj of psi t. And this can be computed explicitly, and you just get that it's equal to that. So this is O px of e to the t pi minus pj xj psi t by an explicit computation. So I don't know if sorry if this is uninspiring, but okay. 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 So the next thing I want to understand is the multiplication map. So I have a multiplication map going from H tensor H into H. But I never want to really, or you know what, let's call it the Heisenberg multiplication map. But I never really want to understand the multiplication map, or I want to understand what the multiplication map, but I want to understand it via the commutative, via polynomials. So there is a map into here from polynomials in the variables p and x, and there is a map into here from, so if this is I, j, and k, so this is hm of I, j, k. So these are polynomials in pi and xj, in p and xi. These are polynomials in pi and pj and xj. And if you tensor two polynomial rings, you get the polynomial ring in the union of the list of variables. So basically, the ordering map takes polynomials in pi, pj, xi, and xj into here. And likewise, there is an ordering map which take polynomials in polynomials, so this should be square brackets. So polynomials in pk and xk into here. So really, the Heisenberg multiplication map corresponds to a multiplication map on polynomial rings, not the standard multiplication map. Okay? And similarly, later, I will need to describe co-multiplication, or the antipode, or any composition of these things. And anything I will want to describe, at the end, will be described as a map between polynomial rings. Okay? So, completely forget everything that we've done, or completely forget our specific context. I want a general system to describe maps between polynomial rings. So suppose I have a map L going from the polynomial ring in some set of variables z sub a, So I will think that A is some finite set, I, J, K, L, and then when I will write Z sub A, I will mean variable Z corresponding to A. So Z sub A will be a collection of variables, Zi, Zj, etc. So Z sub A is some finite set of variables, if A is a finite set. And I have a map L going from here into the polynomial ring in variable Z sub B, where Z sub B is some other finite set. In our case, the finite set are pi, pj, xi, xj, sorry, are written here, okay? So, in such a situation, how do I describe the map L? How do I present, how do I, well, I want to summarize it somehow. So, what I need to know is what is L of every monomial. So I need to know what is L of Z or Z sub A to the power n, where n is really not a single integer, but a tuple of integers. So n, a different way to say it is that n is really a function from the set A into the natural numbers, which tells you for which variable which power it is. And then when I write ZA to the n, what I really mean is the product over all indices in A of the variable Zi to the power ni. Okay? So I have this sequence of things. And this sequence of things, it's not really a sequence, it's a multi-sequence. It's a sequence depending on several indices. So this sequence of things determines the function, the function L. Determines the map L. So when you have a sequence, a standard thing to do in combinatorics is to look at its generating function. So I want to do exactly the same. So, so in combinatorics, often if you have a sequence A1 or A0, A1 up to A, and so on, often you encode it by considering the generating function. So you choose some variable alpha, and you write sum of a n alpha to the n. So one standard example, so this is the so-called generating function. So one standard example is the Fibonacci number. So you define f0 equals to 1, f1 is equal to 1, and then fn is equal to fn minus 1 plus fn minus 2. I'm sure you've seen this. And then the generating function, so let me introduce the notation. So calligraphic G of a sequence will be this thing applied to the sequence. So the sum of fn times, so you see, if the sequence was called A, I would call the variable alpha. if the sequence is called f, I would call the variable phi. So my convention is always to go from Latin to the corresponding Greek. Okay? So what is this? So, do you know? So that's like a standard game that people play in combinatorics. So it's 1 over 1 minus phi squared. And anyway, so this rational function in some sense encodes the Fibonacci number. If you look at the Taylor expansion of this function, it includes in it is the Fibonacci sequence, and so various manipulations to do with Fibonacci numbers can be done instead by manipulating this, and that will also be our strategy. There's actually a slight difference. Maybe I should have called it G standard, because there is also G exponential, and G exponential of a sequence is exactly the same thing, except instead of just Fn, you divide by n factorial. So you look at this sum. Okay? By the way, let's do an example. So what's the standard generating function? The standard generating function of the sequence 1, 1, 1, 1, just the sequence, the infinitely repeating sequence of ones, but now I have no canonical choice for the variables, so let's call it alpha. Okay? So this is sum of alpha to the n times 1, but that's a geometric series, so it's 1 over 1 minus alpha. And what is the exponential generating function of the same sequence evaluated at alpha? So this will be sum of 1 but divided by n factorial, alpha to the n. And this is just the formula for the exponential. So this is e to the alpha, hence the differing names. Now, I will always use exponential generating functions in this class. So I will just call it G. Okay, so G of a sequence. Okay? So, so by the way, an exercise for you. So this is the so what is the exponential generating function of the Fibonacci number, and why is this one true? Okay, so exercise compute this and verify that. Okay, so back to our situation. So we have a multi-series of values, and I want to encode them with a generating function. So what I will do is exactly what I've done here. I will choose a dual variable, multiply by powers of the dual variables, and divide by n factorial. So this I will multiply by zeta to the n, or zeta a to the n, where zeta a is, again, zeta I, zeta j, and so on. Zeta a to the power n is defined in exactly the same way. I will divide by n factorial. Well, n factorial, when n is a tuple, is defined to be the product over all i's of ni factorial. It's just the product of the factorials. And that's it. And this will be defined to be the generating function of the map L. Okay? By the way, sorry, I forgot the summation. Sorry. So this is summation over all n, and this is defined to be the generating function of the map L. So, by the way, where does it live? So, where does this thing, algebraically, where is it? Okay? So, this is a power series in the zeta variables whose coefficients are things like this, which are elements in the z variables, in the zb variables. So this belongs to the ring of polynomials in the z variables extended to be powers, the standard notation should be read in the opposite order in which it is written. So this is power series in the variables zeta of A, whose coefficients are polynomials in the ZBs. Okay? Okay. I think this will make a lot more sense if I'll give a few examples. Okay? So, example. So, let L be the map from the polynomial ring in just one variable into the polynomial ring again in just one variable. Let's call it L1. And it's the map which maps L1 of, if you have a polynomial P, it's just evaluate, so it just evaluates this polynomial at z plus 1. Okay, so it just shifts polynomial by 1 unit to the right, to the left, whatever it is. Okay? So let's compute the generating function for L1. So the generating function, so this is a summation over n. This is the ring of polynomials in just one variable, so it's a summation, it's a single summation. N goes from 0 to infinity. We have a single dual variable zeta, so zeta to the n divided by n factorial times L of Zn. L of Zn is z plus 1 to the n. So this is sum of zeta to the n divided by n factorial, z plus 1 to the n, and this is just the exponential of zeta times z plus 1. Okay? Now, this, I didn't change my religion or anything. This is not analysis. This has nothing to do with calculus. This is algebra. This is a power series in the variable zeta whose coefficients are polynomials in Z. Okay? There's no calculus here, only algebra. Okay. By the way, I should have started with something even simpler. What's the generating function of the identity map? So, again, it will be sum n goes from 0 to infinity of zeta to the n divided by n factorial, z to the n. But this is just e to the zeta z. Okay? And when you look at this, so it does look like you took the generating function from of the identity and replaced z by z plus 1. And this is general. So let's just write this. So you see, the thing written here, well, so, okay. L is an operator acting on polynomials in Z. But I can extend the ring of coefficients to include the zetas. Right? I can always tensor this ring, or I can extend the ring by allowing power series in zetas. So if you know, I can extend this by allowing power series in the zetas. By simply acting on the coefficients, by preserving the zetas. And if I do this, I can bring the zetas into L, and also the summation. So this becomes L of the sum over n of 1 over n factorial, zeta a to the n, za to the n. But this is exactly the definition of the exponential function. Except it's the exponential function, well, this is a multisum over multi-n. So this is the exponential function of the sum. So this is really L of the exponential function of the sum of zeta I zi. I runs inside A. Okay? So maybe I'll do one more example. Yeah, I have time for one more example. So, what is the generating function of the map between polynomials? Sorry, the generating functions. So you know what? Let's say L2 of a polynomial is the derivative of that polynomial. So what is the generating function of L2? So the generating function of L2, well, let's compute it in two ways. By the formula written here, it's L2 of this thing. So this is L2 of e to the zeta z. L2 is just differentiation. So I differentiate e to the zeta z, and I get zeta e to the zeta z. Alternatively, I could go directly from the definition. So on the other hand, this is the sum over n of zeta to the n divided by n factorial, L of z to the n. This is, so L of z to the n is n z to the n minus 1. So this is the sum over n of zeta to the n divided by n factorial, n z to the n minus 1. And this summation starts at n equals 0, but if you start at n equals 0, you get 0 here because of this n. So let's start it at n greater, so I can rewrite it as summation as n greater than 0. And this is summation over n greater than 0 of zeta times zeta to the n minus 1 divided by n factorial is n minus 1 factorial, and z to the n minus 1. Now, I can pull the z factor out, and I'm left with the formula for the exponential function. So, sorry, the zeta factor out. So this is zeta e to the zeta z, which fortunately is the same thing. Okay? Okay. So I'm out of time. But the trick will be, we will replace everything with its generating functions, and then we will learn to work with generating functions. Okay, so see you on Friday. Okay.